In our season premiere on K-means, I criticized the approach for its propensity to find clusters that aren't necessarily intuitively pleasing to me, at least when the data gets far from the idealized Gaussian blobs that clustering algorithms see the world through. If your data isn't ideal for your algorithm, a common approach is to transform the data into a more useful form. That means at the very least a mapping of some kind, but more productively a dimensionality reduction, for which you actually have many different options. In this episode, I speak with Sybille Hess about her work applying matrix factorization in this context.
I'm Sybille Hess. I'm assistant professor at the TU Eindhoven. I got my PhD in 2019 in Katharina Morick's lab in Dortmund. And during my thesis, I have been working mostly on matrix factorization and in particular matrix factorizations, which are clustering objectives. But recently, I actually wanted to answer also other questions regarding deep learning.
Gotcha. And for listeners who don't know, can you expand on the relationship between matrix factorization and deep learning? What are the mathematical foundations that they share?
Matrix factorization and deep learning is a bit difficult. What is kind of easy to intuitively grasp is, for example, matrix factorization and autoencoders. So in autoencoders, you have this idea that you have your input, right? And then you have layer after layer, and you have always fewer nodes at each layer. And the idea is basically that you map towards a compressed space in which most of the information is still maintained. And then you map from your compressed space, which is also called embedding, onto the original space again. And the task is basically that the input is then similar to the output. And this idea of having a compression is like funded by matrix factorization, basically. So like one of the most popular matrix factorizations are, for example, singular value decomposition or the eigendecomposition. And most researchers maybe have already summarized their data by a matrix factorization. The idea is that if you have any matrix, that you might not need all of the information of that matrix. You don't have to store the whole matrix. Instead, you can compute a low-rank product, which captures approximately what the matrix elements are. And then you have a representation of your matrix, which is lower dimensional. So because autoencoders are different to matrix factorization, so what the main difference is that in matrix factorization, you have your data, which is given, for example, in a tabular format, and then the matrix factorization computes a new basis, so new basis vectors which expand a new space in which your data is then represented by the coefficients which are actually given by the other matrix. And so every data point gets its own coefficients in matrix factorization. But with autoencoders, you actually compute a function which maps every input onto the embedded space. So basically, every input is handled with the same function in autoencoder learning, whereas in matrix factorization, you don't have this function. You just have the factorization itself. It's a bit difficult to explain.
Yeah, no, but I think that helps a lot. When I think of matrix factorization, I'm thinking of something very formal. I'm going to use an algorithm. It's going to be deterministic. And because it's a very mathematical process, I get certain, benefits. I can make strong statements. Maybe I know about it asymptotically or completeness and these kinds of things. And it's very, proper. But then when you look at, an autoencoder or deep learning in general, it's kind of like all the rules are off. Just go try optimize and see where you end up. Do you find that the solution that process finds are comparable to the algorithmic procedures, or are they finding new and interesting ways to arrive at a compressed version of the data?
What deep learning can do is it learns this function into this embedding for you. And with matrix factorization, what you do is you rather define your kernel beforehand. So for example, what you can do is if you use, for example, spectral clustering, which interprets the data as a graph, which is only represented by similarities. And then what you can do is represent local similarities only, for example, by an RBF kernel. And then you apply matrix factorization, and then you know that matrix factorization, for example, minimizes your objectives. Then you get all these proper results and all these properties about matrix factorizations. But the task is still that you have to define these similarities beforehand. And your result will be also sensitive to the definition of these similarities. Whereas deep learning has the potential to learn these similarities or this some kind of function which maps into these spaces we want, where everything is more easy, but low dimensional.
Well, I would love to zoom in on one of the core contributions of the paper, and that's the formal proof that softmax-based classification is k-means clustering. I think that might be surprising to some listeners. If they've been listening recently, we've introduced the idea of k-means clustering, so we can take for granted they know that concept. But it's not obvious how that connects to softmax. Help me understand this better.
What softmax basically does is it compares the embedded vector of your input to certain other vectors. So these are basically the vectors which are represented by the connecting layer from the penultimate layer to the last layer. So what you do is you learn in the last layer some weights, which are your vectors in the embedded space, to which you then compare your embedded input. And the softmax formula itself then computes some inner product and then applies some other functions to it, but this is not very important. But in principle, what is important here is that it compares the inner products of your embedded input vector and the class defining vector. So every class gets one vector, and then you compare which inner product is the largest. And what that means is that your classification in the penultimate layer, so after you embedded your points, the classes are represented by cones. So it's like a Voronoi cell distribution, but not like many of you probably imagine Voronoi cells with these, really, which look like cells, but it's just like cones, which open with a certain angle and which go then infinitely beyond, basically.
Yeah, so help me understand those cones a little better. What space are they in?
So the cones are in the space of the embedded input, so in the embedded space, which I call the space which you get as output after the penultimate layer. Because they are basically at the penultimate layer, after the penultimate layer, this is where the magic happens in a way, because this is like the final layer to which you apply the softmax, and then you already get your results. You don't do any more mapping or so. In this embedded space, the class is then equal to cones, and actually there's a property of the inner product that it's the angle of a vector times the angle of the two vectors which are compared times the norm of both vectors. So the larger my embedded input is away from the origin, the higher will be the confidence, because then the inner product will be high, which in itself doesn't really make much sense, that you would say that the confidence gets higher the more like the mapped input goes to infinity. But this is one of these very weird properties of using softmax in deep learning.
So when I think about an embedded space, generally it's not interpretable to me. These are just numeric values in some very compact and useful space, but I can't necessarily tell you much about them. Although all these softmaxes, they seem to be functions operating on that space. Is that a fair way of looking at it?
The embedded space is like, we don't know what kind of space this is, but we know that in this embedded space, the classes are distributed by cones. This is all we can say.
Got it. And now map that idea of the centroid onto this as I try and connect it to k-means. Where is the equivalent to that classic centroid?
Okay, so if you imagine like just arbitrary cones, then maybe it's not super clear intuitively that this is always happening, that this can always happen. But what you probably can imagine is that if you have centroids which are on a circle around the origin, that the Voronoi cells induced by these centroids are actually cones. So Voronoi cells, the set of all points which are mapped closest to the centroid. No, wrong. So Voronoi cells are these cells which you get when you map every point to the class or cluster which has the closest centroid. And then you can map these class boundaries, which are then just linear functions, basically.
Aha, so I see the mapping now, I think. In a certain way, would you say that means this is a special case of k-means, or is the equivalence deeper?
Yes, it is a special case. It's actually spherical k-means. So what our result was that actually it also holds the other way around. So for the situations we usually have in deep learning, where you map into an embedding which has at least a dimension equal to the number of classes, that in this case actually you can find centroids which lie on a circle around the origin, which induce the classes which are the cones.
So this is a kind of a novel equivalence. As we start out, I was saying, I wouldn't have naturally come up with this. So you guys had to sort of discover this idea, or maybe it's been emerging in the literature and this is the most formal example of it. But what do you do with this as a mathematical tool? How do we leverage this result?
So one of the recent empirical observations was that points actually cluster in the embedded space. So that means that there is some kind of structure which equates this picture we have. For example, 4K means that you have one centroid and then the cluster points are closely around that centroid. And this has been empirically researched and shown that this is actually happening in deep learning. So that in the embedded space, you have a structure which is not just like the structure of the cone, that you basically have your mapped input points lying everywhere. So like going to infinity maybe or something like that, but that they actually have clustering properties. And this is also what I found after preliminary study of like visualizations of the penultimate layer and what happens there. Because I was actually quite interested what the structure is like. My first hypothesis was that there might be something like a garbage cluster. So something where points are mapped to which has approximately low confidence around the origin. But that was actually not true. But then instead we found this result that actually these empirical observations that data points like your training data set clusters in the embedded space, that this is also theoretically justified by this notion of centroids which induce actually the classes. So what you have then is that your deep learning model basically is like performing one of these k-means optimization steps, which is just assign every point to the class which has the closest centroid. And if these data points now cluster in this penultimate layer in this embedded space, then that means that it doesn't make sense to assign a high confidence to points which are outside of that cluster. So the idea is that if my training data set is all in one specific region, then it wouldn't make sense to assign a very high confidence if I get now a new data point, which is mapped very, very far away from all the other data points. So the leverage, or like what we could gain from this research-wise, is to actually learn where these points cluster and then reflect also in the confidence like this is actually falling into the cluster of my training data points. So I can say actually with confidence that this belongs to this class. With I mean here now the neural network. Or it's like far away from all clusters. And then you say, okay, this is probably something I've never seen. Usually my training data points do not map so far out in the outskirts. So I would assign a low confidence to it. And this confidence is a problem you see also, for example, if you train just like a neural network on MNIST, and then you just insert a picture which is a noise. So there's no number, it's just like static noise. But then what you will find is that it will be very confidently assigned to any class. So like, I don't know, with 0.9 confidence to the class of 2, of the number 2. But yeah, of course, this doesn't make sense. And we also don't want that, right? We want a neural network which knows what it has seen, or which really can estimate like what it knows, what it can classify and what it can't.
Right, and also not be susceptible to these adversarial attacks. It's surprising that some of these models with just maybe one pixel changed can give not just the wrong answer, but often a ridiculous answer that the attacker has forced it to choose. How can these techniques help us fight against those efforts?
For me, adversarial, like making a method which can handle adversarial learning, like which is robust to adversarials, I think that's like the golden horse in AI at the moment. Of course, I also don't have like the answer to it, because if I would have, then we would have actually models which kind of can make sense of what they see. But yeah, this is still one of the really big questions. And the answer that we found to it is actually that the clustering approach, where you actually measure your confidence by means of the closeness to the centroid, that this can be also used to derive a guarantee on your robustness. So you can compute then for your neural network, like, okay, how far are my centroids apart? So like how big is the margin basically between two classes? And then another component which is needed is also the Lipschitz constant. But there it gets difficult, because estimating the Lipschitz constant is really hard and largely an unsolved problem. But there are methods to estimate it, but they're not, I don't think they're really there yet. They're not super amazingly tight, these bounds yet. But there are methods to estimate the Lipschitz constant, and this is an active area of research. And then given those parameters, then you can actually compute a guarantee, so which says basically that if your confidence is at least that high from your data point, then it will be so and so hard to adversarial attack successfully.
Do I end up paying any computational cost to gain that benefit?
Yeah, so training as this new confidence offers one problem, and that is we did not want to actually have probabilities of class assignments, because actually probabilities we found are usually hard to calibrate, in the sense that you then also get for outliers, so points which are obviously not belonging to any of the classes, that you get for these outliers actually like the same low probability for all of the classes. This is quite hard to obtain in general. So our idea is that the confidence will be between 0 and 1. And then if we have an outlier, then we want to have a confidence of 0 for all classes, basically. So when we do not have probabilities reflecting the confidence, then we cannot use the widely applied cross-entropy loss. Instead, we have to find new methods to actually minimize our loss function, or new methods to define a loss function which is suitable to reflect these clusters. And minimizing this loss function does not require much more effort per se, because it's just a loss function. There's nothing wrong with it. But in practice, we do observe that it needs a few more epochs to actually converge. And sometimes also we need a warm start, so that we initialize our network with a cross-entropy learned neural network for a few epochs or so. So yeah, it takes a bit longer to converge at the moment, and I think this would be a question of further research to actually find a loss function which suits the optimization of these cluster-based classes the best.
Thanks to our annual sponsor, Weights and Biases, the developer-first ML platform. Weights and Biases is an enterprise-grade platform that gives you experiment tracking, dataset versioning, and model management. Their solution integrates with TensorFlow, sklearn, XGBoost, Hugging Face, and literally every other framework I could think of. Integrating with your model training process takes just a few lines of code, and there's even a nice live notebook on their site that'll show you how to get it going. Once your machine learning code base or notebook is wired up, you've just unlocked the next level of productivity. The Weights and Biases platform collects, aggregates, and beautifully displays all of your key metrics and telemetry so you can track your model training in real time and compare different runs. Have you ever had to screenshot a matplotlib graph that you drop in an email or in Slack to show your boss the results of your work? That's like serving a gourmet dinner in a cardboard box. With Weights and Biases, all of your collaborators can see the results of different runs with an idealized interactive suite of tools. You no longer have to be the single source of truth for your whole organization about how the model's doing. If you're on or leading a growing team of machine learning practitioners, you need to investigate if Weights and Biases is the right solution for you. Get started at wandb.me/dataskeptic and mention us when you request a demo. Well, I would love to go under the hood a little bit more. If we went down into the code and an older network might have had a softmax layer, what do you take out and what do you put in its place?
What I take out is just the softmax, the application of the softmax at the end. And instead, I use our confidence measure, which reflects how far away it is from the learned centroids. And the centroids are again given by the connections between the penultimate and the last layer. And from training side, I just take out the normal cost entropy loss, but instead I put in our loss, which compares the classification based on the centroids to the given labels. And yeah, that's it already. Everything else stays the same.
And can you speak to the implementation challenges, if any? What does it take to get that going in? I think you're using PyTorch?
Yeah, defining a loss function, which kind of makes sense, was actually quite hard, because what I first wanted to do is to apply my knowledge from clustering and have a clustering inspired classification loss. But when you come to clustering and deep learning, and also this is a problem in deep clustering, you have just one thing which you get trapped in quite often, and that is that sometimes the solution can be just embed your data into nothing, and then you get nothing back and everything's fine. There are some traps in clustering objectives when you want to learn any embedding. Sometimes you get a very trivial embedding, which is obviously not what you want, but still, just because it exploits some kind of loophole in your loss function, which you did not think of, that it actually minimizes your loss. One of the main problems was really to find a good loss function. But apart from that, we have good documentation of neural networks implementations, and I could just start with whatever we had and then try.
Once implemented, you can also get some of the standard architectures out there and do some empirical tests. Can you walk me through some of the results that you have?
Yeah, so what we have done is mostly we have compared the gained accuracy we get with our new model and the new confidence with the obtained average confidence and the successfulness of adversarial attacks. So in the archive preprint, we had just a few results. No, we got just more and more. So what we had was, for example, a comparison to the one-pixel attacks, but we also later actually added Kalini and Wagner adversarial attacks and also the fast gradient sign method. And what we found is that the confidence can be compared to traditional neural networks. So traditional neural networks are a bit overconfident in general. So what you see in our results is that the confidence will be closer to the accuracy on the test data. And the adversarial attack success is also decreased by a factor which depends then on the data set and the method, but it is observable. We also looked, of course, into the results. So we plotted, or we returned some of these images which were misclassified. And what you can actually see is that the images which are misclassified by our clustering-based confidence do have some similarity with the corresponding class which is wrongly assigned to. So you see, for example, while for the standard deep learning with softmax, you can more or less attack any image and make the network return any other given class. For our networks, there is some kind of connection usually between the classes which are switched. So for example, a dog in a certain lighting which is then misclassified as a deer.
So I'm looking at the archive version, so I don't see, I guess, as rich a result set as you're describing. But what jumped out to me right away is that the accuracy is equal or better than the traditional network. The confidences seem more in line. As you said, neural networks always seem very overconfident. And most importantly of all, I think, is the success rate on the attacks is significantly lower. With all these factors in mind, is there any reason we wouldn't see a broad migration to using a Gauss network in a replacement of a traditional network? It just seems like a win.
Of course, I think that this is itself quite promising, first of all, just because it makes sense. It makes more sense than using the softmax confidence with all its problems. It makes just sense to map our data points close to a centroid and then gather in my mapping to the embedded space together the information of what I have seen and what I do not know. This is just not given in softmax. So this itself for me makes it quite valuable and makes it promising. And then, of course, the results look good. You could maybe say that you can also do some adversarial training or so, and you would also get more robustness to attacks. But generally, these defense methods are not really solving any problem, because usually when they work well, then you have a low accuracy, and when they do not work well, then they do not work well. So if you have a high accuracy, then they're not very robust. And I also think that the indication that there might be some semantic information in this embedded space might be quite interesting, because another idea would be, okay, maybe we just don't need one centroid per class. Maybe we can use 2 centroids or more per class. And then we could also cluster within one class our data points. And I think that might be quite useful also to get more interpretability about your network, because then you can have which images, for example, are mapped very closely to the centroids within one class. And then you can get maybe an idea about how your networks work, like how they identify elements of your class.
This is an interesting idea that clustering can help us better understand the embedded space. Are you seeing a lot of research in that direction, or are these new ideas?
I don't see a lot of research into that direction particularly. There are some papers which emerge right now quite frequently, which have just like we look at the penultimate layer and then suppose other ways to classify in the last layer. So for example, by k-nearest neighbors and so on. One of the things I would find most promising, or which is for me like something I would really like to work on in the future when I have some time again, would be to explore this connection of clustering and deep learning and spectral clustering, because One of the most disappointing results for me regarding deep learning was a paper which identified that deep neural networks cannot learn shapes. So, for example, the shape of a dog or shape of a cat. So some things which are just very natural for us humans to use as a classification method. Neural networks just don't use that. So neural networks are usually more based on identifying textures. So if you give a cat something in the form of a cat, if you fill this with the texture of an elephant skin, then it will classify an elephant. So spectral clustering is used in image segmentation. So it's like a method which can actually do this, identify shapes. And if we have this connection from k-means and deep learning, and spectral clustering is also closely related to k-means, so then what my hope is that we can somehow work on the architecture of our model such that you get something which has a spectral clustering component and can hence learn to classify by shapes.
Interesting. What is it about spectral clustering that helps it find image segments? Just at a high level, how is it able to accomplish that?
Yeah, so in spectral clustering, you interpret your image as a graph. So every pixel is a node, or you can summarize also multiple pixel localities as a node. And then you have similarities in your graph, which are the edges. So the weights of the edges are the similarities between the pixels in your image. And similarity is then just measured by the similarity of the RGB values or something like that. So spectral clustering then identifies clusters within that graph. And spectral clustering, a cluster is defined as something which is easy to cut out. So there you have already this kind of notion between spectral clustering and images. So it identifies these connected shapes which have similar colors.
So on the deep learning side, do we apply that same technique to transform our data into a space where the edges are now realizable by the traditional neural networks? Is that the general approach?
Yeah, and the general neural networks, I think there's nothing like that explicitly. You have just these convolutional layers which are good for translation invariance. And there's also some work on making neural networks, for example, rotational invariant, so that if you rotate an object in an image, that it then will still be classified as the original image. Yeah, so this already, like the rotational invariance, for example, is already pushing the neural network into something which is more shape-based than just texture-based, right? But still, this problem is generally still unsolved.
Well, what are you most excited about when you think about the research opportunities in the near future?
Well, I'm most excited about starting actually this line of research. So we have put this paper on arXiv in 2019. So it's quite a while ago. Usually my papers get accepted in the first go. I've never seen something like that. So we have submitted this to a couple of conferences, and it was quite hard to publish it. And one of the often made remarks we got was that it's basically folklore, that the penultimate layer learns this k-means like distribution of classes. But this is just a bit hard to work with because nobody knows any reference for this, but still we are supposed to say that this is all known, which makes it a kind of a weird feedback, which is really hard to incorporate. But I'm quite confident that after we edit also some ImageNet experiments, that we will find the time to actually polish the paper and submit it again and get it accepted. And then I would really like to see also what happens if we have multiple centroids, and what is a bit further out in the future is to explore this connection to spectral clustering.
Yeah, very interesting ideas. I look forward to following that as well.
Thanks.
So where can people follow you online?
They can follow me on Twitter. I'm periodically quite active. So my handle is @Sybille, or on my website, which is the 0 Shades of Grey website on GitHub. It's you can see it maybe over my GitHub repository, or it's also in my Twitter bio, where I will publish all my teaching material, but also the material of the upcoming tutorial on matrix factorization with binary constraints. And I'd also like to start a blog, but I just didn't find the time yet. But as soon as I will publish some posts there.
Well, looking forward to it. I will have links to all that in the show notes. Thank you so much for taking the time to come on the show.
Thank you.
That concludes another installment of Data Skeptic K-Means. Thanks to our sponsor, Weights and Biases. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, show notes written by David Abembe, and our host, Kyle Polich.